We found out last lesson that cells and batteries actually have resistance. Today what we're going to do is we're going to measure the resistance of a cell. So it's called the internal resistance, and sometimes in questions they say the internal resistance is negligible, and you've probably seen that in questions I've given you so far. But when it isn't negligible, we can draw it like this. So we just draw the symbol for a cell next to a resistor, and then we can draw a dotted line around the whole thing. That's our cell. These two things, we're splitting them up in theory, but of course in reality the resistance is part of the cell. It's just because the electrons need to move through. If you think about here, we've got an electric field, haven't we? We've got positive side of our battery, negative side. For the electrons to move, let's talk about actual current rather than conventional current for now. The electrons in your circuit, they move this way, right? Which means that the electrons in the cell have to move from the positive side to the negative side. So there's a kind of pushing force through there, but there's some resistance that's opposing that motion, and we are going to measure that today, because we're going to measure the internal resistance of a cell today. So this is how you draw that. If we had a perfect voltmeter, then we could measure the EMF of the cell. So that's the electromotive force. That's the voltage when the current is zero. If we had a perfect voltmeter, we could just set this up and we could read off our perfect voltmeter the EMF of the cell. And sometimes in a question they'll say a voltmeter with infinite resistance, in which case you can just do this. But voltmeters don't really have infinite resistance. They've got a resistance of about 3 million ohms. So we're not going to measure the EMF of a cell directly in practice, because it's too much uncertainty. So we're going to do an experiment to measure the EMF, and also whilst we do it, we're going to measure the internal resistance of a cell. So we're going to set up a circuit. It's going to be a circuit where we want to, we're going to do this by what's called a graphical method. So we want to change something and measure something else. What we're going to change, I guess, is the current running through the circuit. And so we're just going to check what that current is using an ammeter. So to change it, we're going to use a variable resistor. It's going to change the current going through the circuit, and we're going to measure the voltage. Let's think back to when we first learned about EMF and internal resistance then. We've got this equation that the EMF of a cell or a power source has got to be equal to the, I'm going to go for the voltage that in our external circuit. So the energy, let's say, we could call it the energy of the components in our circuit are using, plus also the energy that the charges need to get through the cell itself. So this term here, I like to refer to as lost volts, and I think that's a clearer way of identifying it. This is your external voltage, this is the lost volts, it's the potential difference that's lost in the cell. It doesn't mean it's the potential difference over the cell. Okay, so we can get that into the form that's on the formula sheet, that the EMF is equal to the current times the external resistance, that's this term, right? Plus, of course, the current times the internal resistance, and that's this term, that represents the lost volts. And on the formula sheet, then that's written as that. Incidentally, these epsilons, try and make them look like they're not E's, because otherwise you're just going to get confused, especially when we do electric fields later on. Okay, so we've got this equation, but actually, and I'm not going to bother to rearrange it in the video, but you can rearrange that equation so that it is in the form of V equals minus I little r plus epsilon. And this is the equation that we're going to use, because of course we're changing the current, we're measuring the voltage, and what we want to find out from our experiment is the EMF, epsilon, and little r, the internal resistance. So we can do that. I've deliberately arranged this so that I can get the thing that I'm changing in my experiment, and I can have it on my x-axis, and the thing that I'm measuring, and I can have that on my y-axis. And you can see where I'm going with this. If I write the formula for a straight line out here, I'm going to expect then, if I plot a graph of v against I, I'm going to expect to have a negative gradient. That gradient is going to be equal to the internal resistance, or I should say actually the size of that gradient will be equal to the internal resistance. It's a classic exam question actually, because they often ask you what the gradient represents here. The gradient represents minus r, it doesn't represent r. So students so often write the gradient's the internal resistance. It's not. The negative of the gradient is the internal resistance. And our intercept C is actually going to be the EMF. So we're going to plot a graph of potential difference against current, get this graph. The gradient will be the negative of the internal resistance, the intercept will be the EMF, and then we can hopefully get some good results. To get our power source that we're going to measure the internal resistance of, then we're going to take the ray box, and we've got this battery pack that's on the back, so we take that off, and this is the bit that we're interested in. It might be an idea just to check what's inside, because the reason I'm asking you to do this, not just use any kind of battery from home, is that actually alkali batteries have got quite a low internal resistance. It's quite hard to measure it. But these cheap batteries that we quite often use in the science department are zinc chloride batteries, and you go look, it says zinc chloride on there, I don't know if you can see that. They've got a much higher internal resistance, and so we'll get much better data for our practical if we do that. So we're going to use these. We don't need to take them out of the case. Just if you want to check that they're zinc chloride batteries, then you can, but you don't really need to check because I'm pretty sure they all are. But I'll be honest, I haven't checked them myself, but I wouldn't. You'll know whether or not they are, because either you'll get it's about half an ohm, or you'll get sort of 0.1 of an ohm. So this is our battery. This is the circuit diagram we'll be following, same as before. We've got the these plugs here. They're the same size, so you can stack the leads in the back there. I'm actually going to do don't often do this, but I'm actually going to do the voltmeter first. The battery pack also has got an on-off switch, so it's turned off at the moment. I'm going to plug into the voltmeter. I normally do it last in a circuit, but the way this one's set up, I'm just going to do it first. Always plug into COM first, plug into the one with the V on it, because we're using it as a voltmeter. The voltage of this battery pack, so we've got two 1.5 volt cells in here, so it's about 3 volts, which is more than 2. We want this symbol, it's the DC symbol, so we want the DC voltage kind of side of this multimeter. But 3 is more than 2, so we're going to have to go for this 20 to get that on the right setting. At the moment, obviously, it's reading 0, but if I turn it on, yeah, we get a reading on here, so that's good. So that's that. That isn't the EMF, remember, because this multimeter's got a resistance of 3 mega ohms, not infinity. Right, I'm going to plug the ammeter in as well. So ammeter goes into COM first. Remember, we're always going to COM first, and then we want the 10 amp DC. We're going to be measuring quite high currents here, perhaps. Hopefully that's going to work, because I think that if we have to go onto the milliamp setting down here, then we're going to find that quite a lot of the fuses in the multimeters I've given you have blown. So we're going to be using the 10 amp setting. So 10 amp on there, and therefore 10 amp on the dial. And then we're going to plug into the rheostat, but we're going to use the rheostat, or the variable resistor if you want to call it that, just as a variable resistor, so just in series in the circuit, no potential divider going on here. And then the way I've plugged this in is probably not going to look a bit ugly, but that's how I've done it. Okay, so we're going to start off with the variable resistor with the maximum resistance. So thinking about that, at the moment what's in the circuit is this coil of wire here. So I'm going to try and make that maximum. Don't want the circuit on for too long because we're essentially short-circuiting the power supply. So we've got this on-off switch on the actual battery pack itself. So all I'm going to be doing is going to be turning that on, and then if you see the 2 hold buttons on the multimeters, so I'm going to turn it on, wait for them to settle down, press the 2 hold buttons, turn it off, and then record my readings. I think we can work out how to draw a results table, so I'll leave that up to you, obviously. So I've actually got a minus sign on the ammeter there, but you can just either ignore it or change the polarity in the circuit and get rid of that. I'm going to pick different resistances along here. You want 8 values, and then we're going to plot a graph of potential difference against current. After you've got your data, then you're going to plot a graph. This is obviously just a sketch. Now, I'm quite strict with graphs normally, so is the exam board, so that's why I'm strict with them, that your results have to take up more than half the piece of graph paper. If you do that with this, you might find that you can't extrapolate your line of best fit back to the y-axis. And if you can't extrapolate it back to the y-axis, then, so let's say, I don't know, what all our points are here, and we do this, and we're going off the edge of the page here. If you can't extrapolate it all the way back to the y-axis, then you're going to have to use algebra to find the EMF, because the intercept, of course, is the EMF. So we can break those rules for this. We don't have to have our results taking up more than half the graph paper. Try and make sure that you can extrapolate your line back to the y-axis there. And then we can find from our graph the internal resistance and the EMF, and that's what I'd like you to turn in. Remember that we've got 2 cells in our battery pack, and so we're actually expecting to have to halve the value for internal resistance and to halve the value for EMF as well, because they're in series with each other. But and that's only really relevant if you're trying to look up online what's the internal resistance of a zinc chloride cell. As I say, it should be about half known, but quite often it's not. Sometimes it's a lot less than that. It's partly to do with, if we get on our rheostat, if we have this resistance set really low for too long, the battery's going to get hot, and then the resistance is going to go up. So we do want to make sure that our circuit is turned off most of the time, and only turned on when we're taking readings. But as I say, good luck with it, and I look forward to see what you get.